Hello everyone, welcome to the lecture on memory management in operating systems. Today we'll start the lecture one of the most crucial functions of an operating system, which is managing the computer's main memory. Let's start by focusing on the main memory. In this part, we'll cover the fundamental concepts of how memory is organized and protected. To begin, let's establish some background. For any program to run, it must first be loaded from a disk into the main memory. The CPU can only directly access the main memory and its internal registers. The memory unit itself simply responds to a continuous streams of requests, which are either a read request for a specific address or a write request with both an address and data. Accessing registers is incredibly fast, which often takes one CPU cycle or even less. However, accessing the main memory is much slower and can take many cycles. This delay forces the CPU to stall as it waits for the necessary data to execute the current instructions. To bridge this speed gap, a case is placed between the CPU registers and the main memory, providing a faster access to frequently used data. Finally, a crucial concept is memory protection. We must have mechanisms to ensure that a user processes do not interfere with the operating system or each other. This protection is essential for stable and correct operation of the entire system. One of the earlier and the simplest hardware method for memory protection is the use of base and limit registers. For each processes, the operating system defines a specific range of legal memory addresses. The base registers hold the smallest legal physical memory address, and the limit register specifies the size of that range. Together, these two registers define a process's logical address space. As you can see in the diagram, a process can legally access all the addresses from the base value up to the base plus limit value. An attempt by a user program to access memory outside this range is basically an error. So let's talk about hardware access protections. So this protection is enforced by the hardware. For every memory access granted in the user mode, the CPU hardware automatically compares the addresses against the base and the limit registers. Looking at the flowchart, you can see the process. The CPU first generates an address. This hardware first checks if the address is greater or equal to the base register. If it is, then it checks if the address is less than the base plus limit value. If both conditions are true, the access is allowed to the process to memory. However, if either check fails, it means the process is trying to access memory that it does not own. This will trigger a trap to the operating system, which treats it as a fatal error, often terminating the program. This mechanism effectively prevents a user program from modifying the operating system or the user data. Now let's talk about address spaces. It is a fundamental concept in memory management. The distinction between the logical address space and the physical address space. This separation is key to how modern operating system manages memory efficiently. A logical address, which is also called a virtual address, is the address generated by the CPU. This is the address that the program thinks it is accessing. The set of all logical addresses a program can generate is its logical address space. On the other hand, a physical address is the actual address seen by the memory hardware, the one that gets loaded into the memory address register. The set of all corresponding physical addresses is the physical address space. Whether these two addresses are same or different depends on when the binding of the instructions and data to memory addresses occur. In older schemes like compiler time or load time binding, the logical and physical addresses are identical. However, in modern systems that use execution time binding, the logical and physical addresses will differ. And this is where the memory management becomes really powerful.